So this is session F. And this is, we're going to hear from Kevin Ullman on a survey of N2H for the Serpens molecular problem.
All right, welcome everybody. I had a few multimedia things in here that were super awesome, but they aren't going to work today. So if you want to see those after the presentation, just find me around. Anyway, I'm Kevin Hardegree-Ullman. I worked with Dr. Yancy Shirley over in the back. Hi, Yancy. And I did work on a survey of the N2H plus molecule toward the Serpens molecular cloud. And I would like to thank all these wonderful organizations for their help in this research. So what I'm going to go over is the motivation for this research. Why are we doing this? I'm going to talk about the particular molecule that we looked at. I'm going to talk about the survey that we completed at the Arizona Radio Observatory 12-meter telescope on Kitt Peak. We're going to also talk about column density, which is one of the parameters that we could measure from this survey. Also, I'll give some results and some further study that we're going to complete. So this would have been my super awesome video that kind of explains star formation in 30 seconds. But I'm going to have to just illustrate this for you. You see this nice pretty picture, that's a star about to explode and form the Crab Nebula. But what happens when stars explode is they deposit gas into the interstellar medium. And it happens that the interstellar medium already kind of has some gas floating around, and when all this gas comes together, it eventually becomes dense, and it eventually collapses to form a protostar. So we're actually looking at the stages around the collapse time and looking at specific molecules and looking at molecular evolution that helps in star formation. So the N2H plus molecule, this would have been another super awesome animation up here. This is what the N2H plus molecule looks like. It's a linear molecule consisting of 2 nitrogen atoms and a hydrogen atom. And since it's a little bit skewed how it's set up, it allows it to kind of rotate. And most molecules have rotational energy transitions at quantized levels, so we know when energy transitions happen. And we were looking at the first excited state transition to the ground state. And that occurs at 93 gigahertz, which is around 3 millimeters in wavelength. And that's observable using this telescope here on Kitt Peak. It's a pretty cool facility. And this is a particular spectrum of the molecule that we get. This is our brightest source that we looked at, and this is N2H plus, and it shows hyperfine splitting. So you see these splitting components in the spectra. We aren't quite at the resolution. There are actually 7 hyperfine splitting levels, but we didn't have really high enough resolution to be able to see those, and that's due to magnetic quadrupole moments, and it's all sorts of crazy NM and quantum mechanics that make this happen. So the survey that we completed, we read a paper by Melissa Enoch in 2007, and she did a 1.1 millimeter continuum survey just looking at the material in the Serpens molecular cloud. And you can see their map right here, and you can see a few regions, we call them filaments, of star formation. You see cluster A, cluster B, and cluster C. And what we did was, in Melissa's paper, she had identified 35 dense cores, so things that are either stars already or maybe going to be stars in the future. And we looked at all these cores and detected N2H plus in every single one of these cores. They determined that these are protostars or starless cores based on comparing their information with Spitzer data, and that Spitzer data allows us to point out whether something is starless or a protostar. We also created what we call on-the-fly maps of these little rectangular areas, and what that allows us to do is see the intensity of our N2H plus in these filaments. So you can see some contour maps of N2H plus overlaid over these regions from the just continuum survey. And you can see that the N2H plus intensity corresponds very well with the dark regions in the continuum survey. So that's really good to see. So one of the parameters that we can calculate based on our survey is what we call column density. That's basically the amount of stuff that you see in a small unit of area on the sky. So you start off with a column of material, but we're kind of limited to looking at this face on. So this is what we would see if we were able to look face on to this column. So we're just seeing how much material is in this area of the sky. And that's determined by a whole bunch of parameters. And if you want to see the cool equation that we use to calculate that, I'd be happy to show you at the end of the presentation. But you can see in this histogram here the abundance, or the amount or the column density of all these cores, and you can see that in the protostellar cores, there's a little bit higher column density on average than in starless cores. So that's good to know. For some of our results, we determined that N2H plus is a very dense gas tracer. If you saw the contour maps a few slides ago, you'll see that the N2H plus traces very well the dense gas in these filaments. We determined that the more massive the core, the more N2H plus you can see. So this plot over here is column density versus mass in solar mass units, and you can see that the blue points are protostellar sources, and the black points are starless sources, and the higher mass stars have a lot more N2H plus. And we've determined that that's just because all the protostellar stars are just larger on average, and they have a lot more material. So if we had a very high resolution radio telescope, we'd actually see a hole of N2H plus toward the core, and that's because it's a little too hot for N2H plus to exist. But there's a huge envelope of gas around these protostars that you're just seeing a lot more N2H plus. And so also from here you can see that protostellar cores are more massive on average than the starless cores, and that's from a simple Jeans mass calculation, which is the mass at which these little pockets of gas would collapse under gravity. Most protostellar or starless cores have not yet reached that mass. So we will be continuing our study of the Serpens molecular cloud, and it's wonderful that the next talk actually happens to be Kaylin Burley, who worked with Dr. John Beebing on a survey of 12CO and 13CO in the same molecular cloud. So we're hoping to refine molecular gas phase evolution within these molecular clouds to help understand how stars are formed. So that's my presentation. I'd be happy to entertain any questions anybody might have. Is about 50 miles west of Tucson. It has, I think, 24 telescopes. It's one of the largest collections of telescopes in the world, and it's wonderful that it's so close to Tucson. Is that all you know? That's complete opposite end of Tucson. Yes?
On page 7, you have a comment there that is, no, one again there. The envelope around protostars is not yet hot enough to burn off the N2H. Does that imply that once it turns to star, it becomes a star, that the N2H would then burn off?
Yeah, once the star starts to completely collapse and suck in all the gas and the envelope around it, all the N2H plus is going to just burn off. But in most cores, it's only the core area of this cloud of gas that is collapsed. So the core is really hot, but the envelope around it is so large, it's spread out over a few AU, that it hasn't gotten hot enough in the envelope around it.
So you don't see the N2H in the core, you just see it in the surrounding area?
We can't determine that with this survey, but if we had a higher resolution telescope, such as ALMA, we would be able to detect that, and we would see a hole in the middle where the core is.